Hey everyone, I'm Arnab, and this is my colleague Weiwei. We both work at Meta. So today we're going to be talking about scheduler and sharding considerations for network efficiency. But before we get into that, a little bit of intro about myself. I've been at Meta for 6.5 years. I work on the MAST team at Meta. MAST is the ML training scheduler for all GPU training at Meta. And as part of our work in AI infrastructure at Meta, there's a huge focus on AGI. So let's talk about AGI. AGI stands for Artificial General Intelligence. From an industry perspective, there's a big push currently towards AGI. And at Meta, it's no different with our Llama models. In general, we've found that more compute leads to better model performance. And thus, at Meta, we have been investing in large-scale training clusters. So to this end, last year, we built a 24,000 GPU network for training ML models at scale. We ran into a number of scalability and latency problems when building a network of this size. Specifically, at 24K scale and beyond, sharding considerations for the model and scheduling considerations become more important due to the cost of network hops between GPUs in an AI zone. The cost of doing nothing here is that training performance is impacted, which is undesirable. So in this table here, we have, on the vertical axis, we have GPUs. And then on the horizontal axis, we have the various forms of parallelism. And basically, what it's showing is that if we do nothing, as the number of GPUs in a job goes up, the training performance is impacted. So for Llama 3, with careful performance tuning and optimization, we have managed to improve this by 2.5x. So the GPU utilization, we managed to improve by 2.5x. This talk will be broken up into two major subsections. In the first section, Weiwei will be talking about parallelism techniques and model network co-design. In the second part of the talk, I will be talking about scheduling considerations at scale. With that, I will hand it off to Weiwei. Weiwei, off to you.
Thanks, Arnab, for the introduction. As he just mentioned, parallelism is a key technology that unblocks our Llama 3 training at scale. Then I will talk about parallelisms and explain why network and the schedulings are critical for parallelisms. First, we want to understand what is parallelisms and why we need parallelism. So to train a model, we first need to fit the model into hardware memory. For example, in Llama 3 405B model, we will need to use over 700 terabytes of memory. However, of H100 only have 80 gigabytes of memory each. We split the model onto 16K GPUs, with each GPU using over 60 gigabytes of memory. So parallelism is to shard the model onto multiple GPUs. This will introduce communication between GPUs. So parallelism will need to minimize the communication overhead between GPUs. This is critical to ensure that training efficiency won't be hurt by adding more GPUs. There are many different types of parallelisms. They have different ways of sharding the model, and they will introduce different communication patterns. I will talk about two parallelisms and explain their implication on network and scheduling. The first parallelism is called fully sharded data parallelism. Suppose we have a matrix multiplication. X is the input data, W is the weight matrix, and Y is the output. Then with fully sharded data parallel, we will first shard the weight matrix onto different GPUs. Then we will also shard input X. Before we do this matrix multiplication, we need to gather W from all GPUs so that each GPU will have the full copy of weight matrix. Then we do the computation and get output Y. After computation, we will reshard W back to its GPU. Compute stream and the computation stream will happen at the same time. When the compute stream is working on the computation of layer I, which is the current layer, the communication stream can start to prefetch the weight matrix for the next layer, which is layer I plus 1. So as we see in this figure, the communication of weight matrix can be easily hidden by the computation through prefetching. Another parallelism, which is called tensor parallel. In contrast, it will always keep the weight matrix on different GPUs. Each GPU will take the same input data X, but since it only has partial of the weights, we will only get partial outputs on each GPU. Then we will need to communicate the output Y on GPUs. In each model layer, there will be multiple such matrix multiplications, and each of the computation will need to depend on the output of the previous computation. So in tensor parallelism, it will introduce several communications, and these communications will be hard to be hidden by the computation. Now, we just learned about two of the parallelisms. There are also other parallelisms. This table is a summary of the parallelisms we used in Llama 3. As we see in this table, that different parallelisms, they have different communication data size, they have different difficulty to hide their communication by computation, and they will have different tolerance for slow network. As we just learned, TP is hard to hide the communication, and it has a low tolerance for slow network. So for TP, we need to make sure TP will have high bandwidth network. CP has a medium difficulty to hide its communication by computation. PP and FSDP are relatively easier to hide their communication, and they can tolerate slow network. Then how do we choose the combination of parallelisms? So after we can fit the model into memory, we need to minimize the communication overhead for these parallelisms. For example, if the weight matrix communication in FSDP becomes a bottleneck, which means that it can't be hidden by the computation of the current layer, then we can introduce TP to reduce the amount of weights that need to be communicated on each GPU. So looking at these parallelisms and their requirements for network, it is super critical that each parallelism can take the best utilization of the network bandwidth. This is what we did in Llama 3. We used network-aware parallelism. We ordered these parallelisms very carefully according to the hierarchical network bandwidth. We put TP the innermost, which is usually within a rack and can utilize the high bandwidth scale-out network. CP is the next. It will be cross-rack communications. PP is the second outermost. We try to keep all the PP communications within the same AI zone. FSDP is the outermost, and the communication will go across AI zones. But what will happen if we didn't schedule the GPUs accordingly to the parallelism and the network hierarchy? This is an example. In this figure, the two yellow dots, they are in the same tensor parallel group. They should be in the same rack. However, they are placed across AI zones. Then the communication between these two GPUs will be super slow. And this will also introduce slowness in this whole TP group. Since there will be a synchronization point at the end of each iteration, then any of the slow group will slow down the whole training. Now we learned that it is super critical to schedule the GPUs accordingly to the parallelism and the network configs. I will hand over to Arnab, And he will tell us how we tackle the scheduling problem at Meta.
Thank you, Weiwei. So we will now talk about scheduling considerations at scale for ML training and how we account for these different types of parallelisms in the scheduling layer. So earlier, we had talked about how we had built a 24K GPU network last year at Meta. The cost of internet communication between GPUs with such a large network goes up the further away in the network topology the GPUs are located. Specifically, even RDMA-backed networks have to obey the laws of physics. Nodes in the same rack have the fastest bandwidth and latency, while nodes, for example, in the same AI zone, but not within the same rack, will incur higher bandwidth and latency. And finally, nodes that are in different buildings that are communicating via the NICs will incur even higher bandwidth and latency. We measure the latency via a metric called RTT, or round trip time. And in general, what we have observed is that increased RTT leads to slowdown in training. So as Weiwei was mentioning earlier, large training models cannot fit onto a single GPU, and we hence break them up into what we call ranks. A rank is simply an identifier or index in a process list, in a list of processes, with each process running on a GPU for ML training. Ranks with slower indices communicate more often, and we thus want to make sure that ranks with closer indices are topologically located closer in the network so that we get best training performance. So speaking of ranks, we have to now assign ranks to hosts just to ensure that we get best training performance. In order to do this, we have to topologically sort the hosts so that network hops between consecutive ranks are minimized. Rank assignment has been rolled out for MAST, and this has enabled cross-zone communication. So let's talk about bad rank assignment. What happens if we don't worry about this? So in this example here, we have 4 different GPUs, with the first 2 GPUs connected to the same AI zone, and the other 2 GPUs located in another AI zone, with both AI zones located in the same data center. So you can see here that GPU host 1 is talking to both GPU hosts 3 and 4, and so is GPU host 2. So this results in higher cross-zone communication latency, and we also have lower bandwidth available due to oversubscription of higher-level network switches. So in order to place hosts with a higher communication rate closer together, the scheduling system needs to know about network topology. So every GPU on the backend network has an associated rack, row, and AI zone ID. This information is fed into MAST, and MAST uses this topological information to figure out how to assign ranks to hosts. So in this case, rank 1 would get assigned to host 1, rank 2 to host 2, and so on. So if we were to do this, then we have a case of good rank assignment, where GPU host 1 is talking to GPU host 4, and GPU host 2 is talking only to GPU host 3. So you can see that cross-zone hops are minimized, and we get a very good performance. At very large scale, rank assignment by itself is not sufficient. As Weiwei was mentioning earlier, we have to ensure that tensor parallel traffic doesn't cross racks, and then pipeline parallel traffic should not cross zones, and data parallel traffic can go across zones and buildings. So MAST is not aware of these parallelism techniques, and this is an intentional design choice that we made. Parallelism techniques in AI tend to evolve very rapidly, and ideally, we wanted to make sure that the scheduling system is agnostic of these. So how do we account for these? So instead of having MAST understand parallelism techniques, instead what we said was, what if instead the scheduling system were to be provided with topological allocation constraints? So for example, you have to allocate in multiples of 2 per rack and 128 hosts per data center. If we were to do this, then the training application at runtime could infer that, hey, these two hosts are on the same rack, and I'll run tensor parallel traffic across them. And for this clump of 128 hosts within DC, I will make sure that I run my data parallel traffic. In addition to this, topological aware scheduling also increases the buffer requirements for MAST jobs. So as I was saying earlier, for example, if we have a topological constraint of 2 hosts allocated per rack and 128 per DC, if, for example, let's assume the pathological worst case, where let's say we have 50 racks allocated, and each rack has 2 hosts, and 1 host were to go down at runtime because of maintenance. In this case, we would have 50 hosts of stranded capacity, and we would need an additional 50 racks in order to be able to reallocate the job at runtime so that we can continue training. Thus, with topology-aware scheduling, we need a dedicated buffer of spare hosts that is also pre-allocated according to the topological constraints to ensure that we have sufficient capacity at runtime for the job to run to completion. In addition to what I just mentioned, there are considerations other than network overhead that we also have to take into account when scheduling very, very large jobs. So scheduling overhead is one, and this is basically tracking the amount of time that it takes from the time that the first trainer crashes to the time that the training application re-enters main. Fault tolerance is another class of problems where we're investigating if parts of the ML training model are not functional, can the other parts actually function independently? And finally, these problem areas overlap. We can't think of these problems in isolation. So we just did a deep dive into scheduling considerations at scale. And with this, I will hand it off to Weiwei for the wrap-up. Weiwei.
Yeah, thanks, Arnab, for this great talk. We now learned that scheduling and the parallelisms, they are super challenging at a large scale. Then how can we get the best throughput from large amounts of GPUs? One way to do this is to do infra and model co-design. We build hardware according to the trend of the model. As model becomes bigger and bigger, we will need to build faster chips and a faster network. However, it will take years to build a new generation of hardware and infra. So model also need to adjust to the existing hardwares. For example, if we have less GPUs connected with scale-out network, this will favor smaller model and will favor a combination of TP and PP as parallelisms. But if we can have more GPUs connected with scale-out network, we can design a wider model and utilize more TPs. And it is possible that we design a model that can have both good model quality and have high training efficiency, that is infra and hardware friendly. To do this, we can build a performance model. The performance model can take model config, training config, hardware configs as inputs, then predict the training throughput of these combinations. Through this performance model, we can select the model configs that can give us the best training throughputs given our current hardware and the infra setting. So it is super critical that infra, such as network and scheduling in the model design, that will need the hard work and the collaboration from all of us. So the takeaway for this talk are, first, network-aware, topology-aware parallelisms and the topology-aware schedulings, they can ensure training efficiency, and it can allow communications across higher network scopes. As Arnab mentioned at the beginning, through the careful scheduling, network, and the parallelism design and the tuning, we achieved very high GPU utilization at large scale for Llama 3. Thirdly, topological sorting ensures that scheduling layer is not aware of parallelism abstractions. This gives MAST a good opportunity to do the work without care about lots of other things. Besides network overhead, we also need to consider things like scheduling overhead and the fault tolerance in our scheduling. So that's all for this talk. Thank you all for your attendance.
Thank you.